In this video, I will talk about another application of Ampere's law. So we will find out the magnetic field due to a current carrying long cylinder. So here we have a cylinder here and it is carrying a current I. And we have to find out the magnetic field outside the cylinder and magnetic field inside the cylinder. And remember, this is a long cylinder and our goal is to find out the magnetic field outside the cylinder and inside the cylinder using Ampere's law. Let's first start with the outside. So when I say outside, let us consider this point here, P. In order to find out the total magnetic field at a point P outside the cylinder, which is at a distance, let's say R, what we do, we draw an imaginary loop here. Okay, so this is an imaginary loop here, a circular loop. This is a circular loop. Now if you look at the magnetic field at each point, due to this current carrying cylinder, the magnetic field will be circling around the loop. That means the magnetic field at each point is tangent to this loop here, that it is circling the cylinder here. And you can find it out by using again the right hand thumb rule. We talked many times here. If you hold the wire in such a way that your thumb points out in the direction of current, then your fingers curl in the direction of the magnetic field. Let me tell you here, just like here. If you hold the wire in such a way that your thumb points in the direction of the current, then your fingers curl shows the direction of the magnetic field. So exactly the same way here, if you do that, then each point the magnetic field will be circling around the circle. Okay, and as we have chosen the Ampere loop to be a circle, then the magnetic field is constant, the magnitude is the same at each point. The second point here is the tangent or dl vector or the elementary length at each point is and the magnetic field are in the same direction. That is, b vector and the dl vector are in the same direction. Okay, the two important points, that b, the magnetic field magnitude, is same at all points on the loop. It's the same, the first point. The second point is b vector and dl vector are parallel at all points on the loop. And this is important because at all points on the loop, it's here at all points. And this is important because if b vector and dl vector are parallel, that means b vector dot dl vector can be simply written as b times dl, because the cosine theta will be 0 degree and cosine 0 degree is 1. All right, okay, so now let's apply the Ampere's law. For by mistake I have chosen writing down the Gauss law. It has to be Ampere's. Law here. So what does it tell you? B vector dot dl vector is equal to mu naught I enclosed. This is the line integral. Okay, and mu naught I enclosed, what does this mean? What is the current that is enclosed by this Ampere loop here, or this closed loop here? So if I have chosen this loop, then the total current that is passing through this loop is I. Okay, because the I amount of current is passing through the cylinder, which is also passing through this loop here. So I enclosed is equal to I. B is constant at all points, and B vector and DL vector are parallel. So I can simply take B outside and DL. And this DL is over the entire closed loop here. That means this is the length. This is the length here. So if I integrate over the entire loop, then it will be the total length of the circle here, which is the circumference. And what is the circumference of a circle? This is equal to 2 pi r. That is exactly here, is the circumference of the loop. And now if I solve for B, then it will be exactly equal to mu naught I over 2 pi r. And this magnetic field outside the loop or outside the cylinder just behaves like the magnetic field due to a wire. So there is nothing difference between the magnetic field due to a long wire and magnetic field due to a long cylinder outside. There is no difference at all. Or to the outside wall, it just appears that all the current is just passing through a thin wire. Okay, it doesn't depend upon the radius of the cylinder. Okay, that's what it says. The outside magnetic field is independent of the radius of the cylinder. All right, it doesn't matter whether it is 5 centimeter or 2 centimeter. The magnetic field outside the cylinder will be exactly the same. Okay, now let's talk about the inside. Okay, so for inside, what we have done here, we're going to use the Ampere's law. Let's say we are interested in finding out the magnetic field at this point P here, which is inside the cylinder. And we have chosen again a loop here, and let's say the radius of the loop is r. And again, just by the symmetry, B vector will be tangent to the circle here. B vector and this DL vector at each point are parallel, exactly the same way outside it. But now what does change here? What does change is the current passing through the loop here. Not all the current is passing through this one. There are some current that is passing outside the loop here. All right, only a fraction of the current passes through this loop here. All right, not all the current. There are some current that is passing outside the cylinder, outside this Ampere loop here, this loop here. So first thing we have to do is find out how much current is passing through this loop here. So in order to do that, if we're going to find out the current is uniformly distributed. The current is uniformly distributed over the entire cross-sectional area. So the enclosed current can be given by J times A, and J here is the surface current density. This is not a charge density, this is the current density here, surface current density. So J is the surface current density. That means current, let me write down here, it has to be current divided by the cross-sectional area here. So this current, the total cross-sectional area is pi r squared here, and it is this current is distributed over the entire cross-sectional area. So the current density is a current per unit pi r square. That's the current density. Okay, and if I know the cross-section area of this loop, then I can find out how much current is passing through this loop here, which is equal to J times A. Okay, the current density times the area of this one. The current density is pi r square. Cross-sectional area of this loop, if this loop is pi r square, so the current enclosed will be pi r square divided by r square. Now apply the Ampere's law here. This is the Ampere's law. B vector dot dl vector, this is a dot product, is equal to mu naught I enclosed. And remember, B vector and the dl vector are parallel at each point. As I mentioned here, at each point the B vector and dl vector are parallel. Okay, because the magnetic field is circling around this current here. It is circling around. So and the dl vector is tangent at that point. So both are parallel at each point. As this is a circle too, as this is a circle, by symmetry, the magnetic field at each point is exactly the same. The magnitude is exactly the same. So I can take this one out and it will have dl vector, and enclosed current here, enclosed current is pi r square over r square here. You can see here pi r square over r, that is coming from here. And the dl is the total length of the loop here, the total length of the loop or the circumference, which is equal to 2 pi r. So if I solve for the magnetic field, I'll get this equation here. And now the magnetic field inside the cylinder depends upon the radius. Okay, that depends upon the radius r. So if I plot this graph and this graph here, this is how does it vary here. So inside the magnetic field varies linearly. You can see here the magnetic field inside, this is inside, is directly proportional to r. That means at the center of the cylinder, that means at the center of the cylinder right here, the magnetic field will be 0, and if it go outside here, it increases, and at this point it is maximum. If I go further from here, then it starts decreasing. That's what exactly is showing here. The inside, the magnetic field increases linearly, and at the surface it is maximum. If we go further, then the magnetic field starts decreasing, as B is inversely proportional to 1 over r. Okay, so the magnetic field is maximum at the surface and it is 0 at the center, and outside it decreases as 1 over r. All right, so here we found out the magnetic field inside and outside a long cylinder by using the Ampere's law. And the one thing I would like to mention at the end, why we choosing the long cylinder, not a short one? The answer is, if we choose a long cylinder, then there is no any fringe field. And if you have a short cylinder, a small cylinder, then there will be a fringe field as well. Here, F-R-I-N-G-E, fringe magnetic field. Or in other words, if you have a short cylinder, the magnetic field and the dl vector will not be parallel at each point. Okay, and that's the reason we have chosen the long cylinder. If it is a long cylinder, there is no contribution coming from the fringe magnetic field. So this is it from this video. If you have any questions, write down your questions in the comment section below, and do not forget to like, share and subscribe the channel.